Hello everyone. So this is the supplemental video that is going to walk you through what's expected on assignment number 3. It's not just that I want to walk you through what's expected, but you really don't know how to do the graphical analysis unless it's explained to you. And if we were in class, then we would actually be doing this lab, and then you would do the graphical analysis. But we're not, so I have to explain it to you through a video form. The purpose of this kind of a question is for you to take measurements and use those measurements to determine the focal length of a concave mirror. So what you're looking at here is, it's called an optics bench, but all it is it has a bunch of meter sticks glued down so that you can measure distances, and then you put different optical instruments in different places on the bench. So we have a mirror on the right, and we have a screen on which an image can be projected, and then we also have an object, which is a candle flame. And what happens is the light leaves the candle flame, reflects against the mirror, and forms a clear, focused image on the screen. And if you were doing this lab, you would discover that if you moved that screen to the left or to the right of where it is right now, the image would not be focused. It would be blurry. And the whole point is that there's a mathematical relationship here between the object distance, or what we call DO, and the image distance, which is what we call DI, and the focal length, but it's only true if the image is clear. So you're given some data and you're asked to analyze the data. By the way, in the video that I showed you in the lesson on mirrors, there was a little video clip embedded within there, and that video that I showed you is essentially what we're looking at here from a different perspective, but you have a candle whose light is reflecting off of a mirror and it's reflecting to a screen, and you get that image of the candle flame. So what we are asked to determine is the focal length of the mirror. And question 1 asks you to perform what's called an algebraic analysis. So there's 2 points I want to make about an algebraic analysis. The first one is you use a formula. So essentially we're going to use the formula that you can see here on the left to calculate the focal length from the data. The second thing though, and it's very important particularly for later in the course, is when you do an analysis using a formula, you do not average the data and do one calculation. What you need to do is a single calculation for each set of data. So if I were to label these sets of data so I can keep track of which is which, I can call this data set A, B, C, D, and E. And you as well have 5 sets of data on your assignment. The data that I have up here is hypothetical, and I guess you know what, the data you have is hypothetical as well because it's not actually measured in a lab, which is what we would be doing if we were in a lab. So what does it mean to say we're going to do an algebraic analysis in this sense? Well, you're going to start off with data point A. And if you want to find the focal length, then I guess you're going to have to take 1 over DI, which is 0.3 meters, and add 1 over DO, which is 1.5 meters. And by the way, it just occurred to me that I believe on your formula sheet, it's written as 1 over DO plus 1 over DI. It doesn't matter the order in which you write those 2 terms. Now I've put in the units here because I'm trying to model for you what I would expect from you on the assignment. You've shown your formula, you've shown your substitution, and now what we can do is calculate the answer. We'll take 1 divided by 0.3 and add 1 divided by 1.5. This, of course, does not give you the focal length. It gives you the reciprocal of the focal length. So we need to take 1 divided by that answer, and we get a focal length of 0.25 meters, or 25 centimeters if you want to put it into some units that maybe make more sense to you. So 25 centimeters. Now, what are you expected to do for full marks here? You have to show one sample calculation, and that sample calculation is what we just did. That is the sample calculation. you're going to need to calculate a focal length from data set B and from data set C and from data set D and from data set E, but you don't need to show them all. So I'm not going to do all that for you here. You would repeat the calculation 4 more times. On the assignment, there's a data table where you can record the 5 focal lengths, and then I also ask you to calculate the average of those 5 numbers at the end. And that's how you're going to do the algebraic analysis of your data in this assignment. Now, how are you going to do the graphical analysis? Number 2 says complete the table below, and we'll get to that in a second, and then perform a graphical analysis as instructed in this supplemental video, which is what we're looking at right now. So let's talk about the data first. It turns out that, like with all graphical analyses, you want to get a straight line. And if you were to plot these numbers, which is the data that's measured in this experiment, on a grid or a graph, you would not get a straight line. But it turns out if you plot the reciprocals of them, you will get a straight line. And you'll see why in a second. But the first thing you want to do is calculate the reciprocals of these numbers. And notice that the units that you get when you reciprocate a distance, the units that you get will be the reciprocal of the units for distance. If distance is measured in meters, then the reciprocal will be measured in 1/meters, which is written in this view as meters to the -1. So what are we going to do? We're going to take our calculator and go 1 divided by 1.5. That's a distance we need to reciprocate. And you get 0.66666. Now, because you're going to plot these on a graph, there is a limit to the number of decimals that are useful to you. And I would probably say that if you record 3 decimals, that's good enough. You may not even make use of all 3, but 3 decimals is kind of a good guideline here. And then you need to take the reciprocal of the 0.3. 1 divided by 0.3 gives us 3.3 repeating. So you're going to enter that in your data table. And you're going to repeat this process. You're going to populate this table with the reciprocals of all of those numbers. And this is the data that you are going to be plotting on the graph. And since the distance between the object and the mirror is manipulated, this column, which is the reciprocal of the object distance, will go on the horizontal axis, which is where we always put manipulated variables. Since the image location depends on the object distance, that means it's the responding variable, and responding variables are always plotted on the y-axis. So now let's walk through what the graph is going to look like. We've got our data up in the top right corner, and we've said that the first column in the data is the horizontal measurement on our graph, and it goes up to 2. And when we look at the vertical dimensions of our graph, which is the second column, we have a data point of y equals 3.3. So you're going to have to scale your graph somehow so that you see all of that data when you plot it. On my hypothetical situation here to explain this, I'm going up to at least 5 vertically, and I'm going up a little bit past 2 horizontally. You'll have to choose a scale that works best for you. By the way, you would label the axes and you would give the graph an appropriate title. I'm not doing that, I'm just explaining the physics to you. The axes would both have units of meters to the -1, because when you look at your data table, that's what we have for units. So now what you're going to do is populate this graph with the data. So if you were to plot 0.667, 3.3, you would get a data point. And I'm not sure if I've talked about this before or not, but when you plot a data point, you should put a dot where the data point is and then put a circle around it. You don't need a big, thick dot like I've drawn. It should be visible, but then circle it. And we can plot 0.8, 3.1. And part of your mark here is going to be how accurately you do plot these points. And you continue to do this until you get all of the data. Now what you discover is that the data falls in a straight line. It may wobble a little bit, but in a perfect world it would be a straight line. And because in a graphical analysis in physics we always use a straight line, you need to take a ruler now and draw the line of best fit. We talked about this in class. Basically, you put your ruler down and you draw a straight line with the ruler that you feel represents the data fairly. Now, before we go on, I want to make a note here. Once again, I don't have a title on this. You need a title. I haven't got my axes labeled. You need your axes labeled. One other thing is, normally we're concerned with the slope of a graph, but we don't care about the slope of this line. Let me explain to you now how the graph is going to lead to the answer. Here is my focal length equation. I've written it backwards, but it doesn't matter. I'm going to rearrange for 1 over di. And the reason I'm rearranging for 1 over di is that's what's plotted on the vertical axis. This goes back about 5 weeks, everybody, to when we learned about graphical analysis. You are always going to want to rearrange your physical equation, which is what we're looking at, your physics equation. You want to rearrange your physical equation so that the variable that's plotted on the vertical axis is by itself. That's pretty easy to do. I'm going to subtract 1 over dO. And I get 1 divided by di equals negative 1 divided by dO plus 1 over f. And I'm going to squeak a negative 1 in there. Instead of saying negative 1 over dO, I'm going to say it's negative 1 multiplied by 1 over dO. Now what I want to do is compare that equation to y equals mx plus b, because it's a straight line. And I love this analysis. It's brilliant, whoever came up with it. If you take a look at what's going on here, 1 over di is what I've told you you're plotting on the vertical axis. So that's our responding variable. 1 over dO is what I've instructed you to plot on the horizontal axis, and that's because that's the manipulated variable. That means that whatever is in front of x is the slope. So the slope of your line should be negative 1. I think this is really interesting. It doesn't matter what mirror you use. If there's a focal length and you do this experiment, you'll get a slope of negative 1. But again, we don't care about the slope because the slope has nothing to do with the focal length, and the focal length is what you're trying to find. So how does the focal length relate to the graph? Well, it's a very nice comparison. The y-intercept of the graph is equal to the reciprocal of the focal length. By the way, this analysis that I'm showing you here, this description and explanation that I'm giving you, verbally and visually, is part of what I would expect in your analysis when I ask you to explain how you're getting the focal length from the graph. So the y-intercept of the graph is the reciprocal of the focal length. Well, that means that the focal length is the reciprocal of the y-intercept. And that's what makes this analysis, quite frankly, so elegant and beautiful and simple. All you have to do is find the y-intercept and take the reciprocal of it, and you have your answer. So literally what you're going to be doing here is you're going to eyeball the graph and read the y-intercept. Now I'm looking at that and I'm thinking that the y-intercept is a little bit more than 3.9, but not much. So I would say that the y-intercept of my graph is 3.91, and it has units of meters to the negative 1, because those are the units that would be labeled on your axis. Well, if that's the reciprocal of the focal length, then I can find the focal length by taking the reciprocal of 3.91 meters to the negative 1. So all that remains is for me to take my calculator and find out what the reciprocal of 3.91 is. And I get 0.256, which means my focal length is 0.256 meters. If you wanted to, you could express it in maybe centimeters to give a better appearance to it. So the focal length of the mirror in this question is 25.6 centimeters. So I hope that helps you out with your assignment. We've got a Google Meet today if you have questions on other areas that we've been working on lately. Friday is a PD day, so I hope to see some of you in our Google Meet this morning, but if I don't, that's okay. I understand you guys are busy. I would just say to you that you should have a really, really good weekend. Take care of yourself, and I will talk to you next week sometime. Have a great day, you guys.